Okay, so welcome guys. Today we have Mohammad Hafezi from the University of Maryland, and he's going to talk us about topological photonics. So please, Mohammad, when you want.
Thank you so much. Thank you for the introduction. I'll be here 2 weeks. I hope this talk will be kind of like an introduction to some of the things that we've been doing in my group. I'll be talking about topological photonics mostly today, and maybe a little bit of a its relationship to quantum simulators, but my group is also interested in that. And Alejandro was kind enough to organize another talk next week. Yeah.
Yes, that's one of my university.
Exactly. So that would be more like quantum optics applied to electronic systems, like correlated electron systems. That would be a mixture of theory and experiment. And the idea is that can you use light to manipulate many bodies state of electron, not just like a two-level system, etc. So,
Sorry, Mohammad.
yes.
Can you try to close the notification?
I will close the notification. Can you, because I don't see any cursor.
There was no way without
Yeah.
Yeah, that's fine. So,
Okay, sorry.
so basically, so that would be more kind of like a real quantum optics and condensed matter kind of meeting each other. It's quantum optics meeting condensed matter. But we kind of decided to do this one. This is a little bit of a colloquium style, but since there are no undergrads, I'm going to go faster. So topological photonics, building block of photonics are resonators, okay, from microwave to optical. These are a bunch of examples. You have silicon ring resonators over there. You have nonlinear oscillators in microwave domain that are qubits. It's a photo from Google, or exciton polaritons that you have over here. Okay. So the topology, then I don't need to really introduce it. It's how it talks about how things are connected to each other, but maybe this is new. Usually people use the coffee cup and a mug and a donut. I'm sick of that, so I was thinking about something else. I thought about something more refreshing, like an island, okay? Regardless of the shape of an island, you call it an island, right? But then if there's a piece of island that is connected to the mainland, we call it a peninsula, okay? Like almost an island. So there are two different words because they're topologically distinct. And then regardless of the shape, you have an island. So now, why can it be useful? You can start swimming around this island. You can start at what point and then go clockwise or counterclockwise. That would be an integer number, right? Regardless of the path that you're taking, it will be always an integer number. And that integer number for peninsula is 0. Okay, so there are two integers related. And the whole point is that can you relate it to a physical observable? And that was the point of quantum Hall effect. Of course, people didn't think about it that way. It was observed, and then people realized it's related to topology. But that's the whole point of topological photonics or any kind of topological physics, that you want to have some integer associated with some observable. So the details of the island, the details of the path that you take around the island would not matter. Your observable, your physical observable, being it conductance, transmission, etc., would be only sensitive to that integer number. So that's kind of the point of the previous stage. So in the case of quantum Hall effect, it was a two-dimensional electron gas. You have a perpendicular magnetic field to it. You look at the conductance in the transverse direction. You apply an electric field in one direction and then measure the current in the opposite direction. And then what the folks realized, von Klitzing and company, there's an interesting story behind it, but that would be for over lunch again. But the key point is that you have a physical observable. This is the Hall resistance, or Hall conductance would be the same thing for two-dimensional system. This is this line. This is this line. it takes values that are given by some fundamental constant e squared and h and some integer number. So regardless of the shape of your gallium arsenide shape, regardless of the temperature to some extent, regardless of how you put the electrodes, etc., it does not matter. It's a robust outcome. And the reason that is a robust outcome is the presence of these edge states that we will come back to it, but very like a high level is that you have the magnetic field, you have electrons doing cyclotron orbit, right? In a semi-classical picture. But then if those cyclotron orbits get close to the edge, they cannot finish their cyclotron orbit. They start to skip, either like this on the top or like at the bottom. So the electrons in the bulk would not contribute to the conductance because they're not flowing. They're like trapped and circling around while the edge ones are conducting, and those are responsible for these conductance. And if you dent the system, imagine that I destroyed this part or destroyed this part, it doesn't matter because I always have a new edge, and then I will go around and then continue my way. And that's why it's topologically robust. So basically, that's where the robustness comes from. And the question that we asked a few years ago, many years ago now, is that can you have an analog of it for photonic system? Okay. So why it's also what might be useful is that in a generic photonic system, let's say a waveguide or a fiber, etc., you have some impurity, your photon comes and it gets scattered back. But it would be nice if you have some robust solutions such that when the photon comes, it would not scatter around the impurity and go back, but instead it will flow and continues its way. Okay, so you can think of them actually as robust solutions of the Maxwell's equation that Maxwell could have thought about them many, many, many years ago. It took us from Maxwell to quantum Hall effect, and then going back to like photons, and then understanding that there are actually these solutions to the Maxwell's equation that are robust against dielectric fluctuation. So the first part of this introduction is really about those Maxwell solutions, which we should have discovered them much earlier, basically. So what's the easiest way to kind of see how these topological states can emerge? The way is to fake the magnetic field. Photons will feel the magnetic field usually because magneto-optical properties are present, but they're usually weak in the optical domain. So instead you fake it. And the easiest way that we realized how to fake it is to use ring resonators, that you couple them together. So you see that these rings are coupled to each other like this. And then if they form in such a way that when the photon hops around each of these squares, if they acquire a non-zero phase, it's as if they're acquiring a phase of an electron going around a magnetic field, a Hahn-Bohm phase that we have. So how can we do that? The idea is super simple. Take two resonators. The perimeter of this one is like, you can think of it as a waveguide that is bent on itself, a waveguide bent on itself. M is an integer, lambda is the resonant wavelength. So it's resonant at lambda wavelength. And then you connect it with another resonator that is m lambda plus lambda over 2. So it's anti-resonant at that frequency or wavelength. So the consequence of that is that if the photon starts circulating over here, these two waveguides are close to each other, so the photon can tunnel to this waveguide and comes here, but it won't go back. It will not start circulating. It will instead go over here, does some rounds, and then when it comes back, it will take the lower path. So when it hops from left to right, it takes the upper path. When it hops from right to left, it takes the lower path. So the accumulated phase would be different if I just put this resonator a little bit asymmetric. If it's asymmetric, yeah.
Maybe you can't have any relation.
As long as the total length is this. Because if they're different, then and if it, for example, if the total length becomes m lambda, then you have three resonators that are coupled resonantly to each other, and that's not going to work. But if the total length is fixed, then the asymmetricity will determine the phase that the photon acquires when it hops from one resonator to another resonator. So it's just what I said in the second quantized formalism. This is a Hamiltonian. A photon hops from resonator number x to x1 with a rate kappa that is determined by how these resonators are uh, uh, coupled to each other, and this phase is determined by this asymmetricity. So now the quiz is that, so Hamiltonian should be respectable, meaning that it should be Hermitian. So this alpha and this alpha should be equal and opposite to each other. But what I just presented is that as if the upper phase and the lower phase are independent because they can take any length. So what's the solution of that problem? Was actually the question that Juanjo asked, because the total length is fixed. So I'm not in the liberty of just choosing any length I want. The total length is fixed. So the asymmetricity will fix this alpha. I have just one parameter actually free. There are not two parameters. This plus this is fixed. So L1 plus L2 is fixed. L1 minus L2 will give you the fix. So that's it. So now if I tile my system, if I have these asymmetric waveguides that are coupling these, you can cite them like site rings and then the link rings. If you tile the system in such a way that this phase would not add up to 0, but add up to something like a 2 pi alpha, then you will end up with this Hamiltonian. So this is the Hamiltonian that I've written over here is just the formal, here can we do this, yeah. So this Hamiltonian is just the formal way of writing what the dynamic in the system is governed by. So it's a linear system. One can diagonalize it, look at the eigenstate of the system. You get the Hofstadter butterfly. So these are the energy states, and this is the alpha, strength of this effective magnetic field. And at each of them, you will get a bunch of states. And in between those states, you will see the edge states, which I will come in a minute. So what we decided was to use the silicon uninsulator technology to make those silicon ring resonators. So what I just showed, this is a real SEM image of a chip. These are rings coupled to each other, but they're asymmetrically coupled to each other. You cannot see it on this slide because the operating frequency here is 1.5 micron. And the resolution is 30 microns, so you don't see the asymmetry point, but they're actually asymmetrically located. So you have that, and you shine light at some specific frequency, you will excite these modes. These resonators are not perfect, they're leaky, so the light gets out, so you can actually measure the wave function amplitude, not its phase. We might be able to measure the phase, but we've never actually tried. If someone gives us money. Okay, so these are the states of the system. Imagine that my alpha is fixed, my magnetic field is fixed. There are some states that appear in between the bulk over here. This for a system on a torus periodic boundary condition. But once it's flat, once it's like a square, then you have also states that appear in between these magnetic bands, these bands, and these are called edge states. Why? Because they're confined at the edge of the system, and then these ones circulate counterclockwise around the system, and those ones circulate clockwise around the system. And one can actually understand why this is the case. We have applied a magnetic field to the system, right? So now, if my angular momentum that I'm going around this magnetic field is positive, then my energy will be positive. If I go around it in the opposite way, then my energy would be negative. So depending on the circulation sign of my photon, their energy would be either positive or negative. But since we have this magnetic field, there is an energy cost from inverting these states into those states. So if you put an impurity in front of this guy, it would like to come over here and get backscattered. But the backscattering state has a different energy, as you can see over here, as the opposite end. So it's costly, yes.
And those states always appear like in blank space in the butterfly. Would one of the three states become an edge state?
Yes. So the question was that I have these bands, and then these edge states appear always between the bands. And the answer is, at least for the non-driven one, it's always the case. And it's actually related to this bulk edge correspondence. But whenever you have these states that have this Chern number, that I won't actually even get into it until over lunch probably. Then you have the appearance of the. There are many ways to understand it. One of them is the Lachlan's argument. The other one is TQFT. Actually, there is a very beautiful way of understanding all this in one formalism. Any other questions?
Yeah. Do they only appear at specific values of alpha, or you can completely configure it?
Very good. Yes, it actually it's alpha dependent. So, for example, for alpha equals 1/2, they touch each other. So there is no edge state. It's a specific, it's a special point. For other alphas, they would also appear at other parts of the effect. In particular, if alpha is a rational number Q over Q, you have Q bands, and then in between them you have the edge. So that was the imaging of the edge state. Sorry, I missed it. So you can actually do an experiment. In the experiment, you can see if you pump the system on the left, the photon comes in. There is an impurity over here. The impurity over here is a missing resonator. It's not even detuned from the system. The resonator is missing, but it doesn't care. It doesn't get backscattered. It actually goes around this edge and then continues its way. So this is a simulation, this experiment. This was our first measurement. And since then, things are much better. But historically, I keep it like this. So this is just imaging to show that these edge states are robust. The next question might be related to the other question was that what is robust? What is integer? There was this guy swimming around the island, an integer number. So what is the integer over here? There is a notion, it's called spectral flow. Which basically means that if you pierce a flux into the system and then that flux goes from 0 to 2 pi, the system should not care. The spectrum of the system of a 0 flux and a 2 pi flux is the same. But in topological system, once you pierce this flux, there is something that happened to your spectrum. Your spectrum starts to flow. And one can actually measure that. And that flow is like, in the beginning is like, your spectrum is like this. Then you change it from 0 to 2 pi, the spectrum goes like this, or goes like that, or goes like that. The spectrum will come back to itself, but how many times it moves, that's an integer. And that's basically what guarantees quantum Hall to be integer. Again, if you're interested in this, we can chat about it, but that was kind of all the introductory part. You can make Haldane model, not on just the uniform magnetic field. You can have a staggered magnetic field. You can have higher order topological states that are not edge states, they're corner states. They're topologies manifested not just in the edge state circulating. You had a question. Or now they're at a corner. There is some work. These are all our groups, but other groups also use this platform to show the generation of topological lasers, whether you can make lasers that are more efficient. I think my understanding is that this is still an ongoing debate is not settled, whether they're more efficient or less efficient than the other ones. And you can also make them reconfigurable. You can have situations that you tune these resonators on and off and have different islands. Okay, so this is that one formality, the one platform, but there are many other platforms. There are these waveguides coupled to each other, free space, also in other domains, like in the microwave domain or modulated space, and people with different platforms are looking at these systems. But now the subject of this talk is, can we go beyond Maxwell's equation? So there's robust solutions of the Maxwell's equation. And in particular, can we have some physics that does not have electronic behavior? But so far, I was just talking about single particle physics. And once you have one particle, the statistics does not matter. So we go. So in order to put this in perspective, I would like to use this diagram, the diagram of quantum optics. A photon number on one side, interaction on this side. So this is like low photon number, low interaction, because the light matter interaction is usually weak. So you can pump the system hard and you can go to this nonlinearity. You can also put it in a cavity such that the light matter interaction is enhanced by the number of round trips that you have in a cavity, and then you go to cavity tubing. So this diagram can be actually used to understand the field of topological physics and where it's going from our perspective. This one is the number of photons involved in this topological system, and this is the interaction strength in the system. So what I just described is that low power and weakly interacting, and we have been moving a little bit along this direction. Also along this direction, coupling it to two-level systems, or even with Rydberg state, such that you can make Laughlin state. This is the work from John Simon's group. So let's start with the simplest one, weakly nonlinear system, but you pump it harder. You have a spontaneous down conversion. So you have effective Hamiltonian is like this. You pump the system, you generate pairs of photons, you absorb two photons, you generate signal on either at a higher and lower frequency. This process is efficient if the energy is conserved and the momentum is conserved. The energy is always conserved, it will take care of itself. But the momentum is not conserved. You have to actually do some acrobatics in optics to make sure that the momentum is conserved. That's called phase matching. So in nonlinear systems, one does phase matching. And one effect, one to use these ring resonators to generate the photon pairs, you pump the system, if you take these photons out, generically you will see something like this. If you look at the joint spectral density of these photon pairs that are coming out. So I pump the system, I have one photon coming in here and one photon coming here, and register its frequency. And I make two devices and I compare them. You see no similarity between the joint spectral density of these photons coming. Why? Because these devices are not identical. When I fabricate them, there is always impurity involved. In particular, if the impurity is very large, then your pump photon will be completely reflected and then goes back. So that's why there is this problem. When you go from one resonator to another resonator, you will see one device to another device, you see a huge difference. And the question that we ask is that, can topology help us? That there is a problem, there is this error dependent or basically fabrication dependent problem, and we claim that these edge states are robust, they don't care about disorder, go around the impurities. And can topology help us? And it seems that it does. So this is again linear regime, but I like this work in particular because I think it's the only work that it has done some statistical analysis of robustness in the system. So what is it? So I look at the transmission or the delay time. How long does it take for a photon to go from one side of the system to another side of the system? And then I repeat the experiment many times. I have 20 devices. I just measure them one after another, and I'll put the spectra on top of each other. So these are different colors. You see that in the edge states, that physical quantity is robust, while if the photon goes to the bulk state, it's not protected. So remember that you had the edge states that they were robust because they could not backscatter. But if you go to some bulk state, there is no notion of robustness. So if you add some disorder, it will easily get backscattering. So this is just like a experimental proof that the robustness is even present in the statistical. So okay, yeah.
What is the difference between short and long edge?
We had our connector over here. So this we call it the long edge, and this we call it short edge. Yeah, just the name.
For the light.
Any other question?
They are both robust. Can you go back and say?
Yeah. So you see, for example, the long edge takes a bit of longer time, and this is we scale it such that we can appreciate these variations. The short edge would have one delay time, and the long edge would have a longer delay. And this is the transmission. So if I repeat the experiment for 1D, you see that from one device to another device, this joint spectral density changes a lot. But then if we do it in 2D, for this topological system, the photon will come out at the specific location that we planned it to, because of this robustness that we just. So this is for generating photon pairs. One can prove that they are actually photon pairs. There is also disorder in the system, but nevertheless we have this strong robustness. It's kind of remarkable because mismatch between the resonators is almost comparable to the tunneling, to the coupling between the resonators. Nevertheless, it would be robust. A very intuitive way, just maybe a take-home message of this talk would be that my understanding is that you have this solution to the Maxwell's equation that is chiral, and it has to be single valued, meaning that if I take the optical path and then calculate how much the photon is acquiring phase, it should be an integer times 2 pi, right? Now, if I put my finger over here, it should deform itself and then just keep this integer to be. Otherwise, my solution is not single valued. So basically, it's that. If I push it harder, then it may jump into m plus 1 or m minus 2. As long as don't push it harder. And so this is the rule of thumb that I said for the coffee. This is the rule of thumb for the topological photonics. This is all linear again, of course. And one can also do G2 correlation measurement to show that these are actually single photon pairs, etc. So that everyone's happy. One can also pump it in an opposite way, not generate signal either with different frequency, but identical ones by pumping it the opposite way. So you pump it with high frequency and low frequency, and you generate this phase in the middle. So you can generate identical times. The next topic that we thought it's interesting, which is basically the same Hamiltonian operated differently, is the optical frequency comb. People are really interested about optical frequency comb because they're like the rulers of time and frequency. You can think of them as in frequency domain as pulses that are equidistant in frequency, or light pulses that are equidistant in time. These are just Fourier transform of each other, as long as there is a phase relationship between these pulses. If these pulses are locked, then these are Fourier transform of each other. The way you do it is that you take a continuous wave laser, some nonlinear material, and then you generate them. Of course, there is a huge interest to miniaturize them, and it's difficult. And there are many platforms. And this is a very nice review by Tobias Kippenberg that you have over here. You pump it with one laser. This is the screen laser. And then you generate a comb that, if the resolution allows you, you can see that they're equidistant lines next to each other. It's not a continuous spectrum. These are actually lines that are finely spaced from each other. So we have a hammer, and we want to see whether we can solve some of the problems of topological frequency. In particular, there are these low efficiency, meaning that most of your power is wasted. It just comes out. It doesn't even generate this comb. You see that's why there is this huge output peak. But this is the input peak, and this is the output peak. See that not much of it is actually used. Then the other one is the lack of tunability. And you have some structure in this frequency comb. This frequency comb, you can have good power everywhere, but maybe you don't want to do that. Maybe you want to have some power over here, some power over here, but then over there you want to actually have a very nice comb, and then over here you have a nice comb. If you want to do spectroscopy and your lines are very away from each other, you want to have resolution around the places where you have the lines, not everywhere, and waste power, especially if you want to do without chip. So, as I said, we came with a hammer, see whether it's possible. So the Hamiltonian is the same as just what I showed, but you operate it in an algorithm, meaning that you have this pump, it generates signal and light there, but then if it's harder, then you can generate more sidebands, and also these sidebands will generate more sidebands, etc., and then you cannot control it. Do you always get this generation? No, because there are a bunch of problems. A resonator, if it has some dispersion, the resonances are not equidistant. Actually, if you just look at the resonator, the resonances are never equidistant. there is some dispersion. Also, when you put power into a resonator, you will shift it, so there has to be a balance, a dance between this gain and dispersion, such that in some specific regime, you will create these frequency forms. And this is what it's needed. Of course, you have to satisfy momentum conservation, and then that's where we think that this topological system can take us. So let's just review what happens in a single ring. In a single ring, you pump the system. This is the detuning of the pump with respect to the resonator, and this is this intercavity pump power. You see that depending on the frequency, if you're at omega p3 over here, you have this soliton. If you look at it in time, it's just a peak that goes around the system. If you look at it in frequency, it's a peak and then a hyperbolic form for other peaks that are coming out in frequency. If you move your detuning to somewhere else, you will get chaos. You'll get these chaotic states. And if you move them somewhere else, you will get these solitons, but now not just one peak, but multiple of them. And they're called Turing roles, Turing patterns. The reason is that Turing actually thought about how one can describe this stripe or periodic things in nature that are emergent. The system doesn't have that periodicity, but because you have some nonlinearity and some dispersion in the system, they will conspire, and then you will get pattern on some animals. So the same thing actually is happening over here. You have some dispersion and nonlinearity, and then you get emergent patterns. So they're not one peak after another. It's just actually the distance here by 12.
So what the time is the distance, then is the length of
The different nonlinearity parameter.
this something that you like if you keep increasing, so the distance will shrink.
You can have different variability.
And what happens as you like the intensity of power goes down, right? You pump up.
Yeah, because then you're off resonant. At some point, you're off resonant. Kind of complicated dynamics, nonlinear dynamics. It's quite time consuming to actually solve it. I mean, for not a single ring, but now for many. So this is this efficiency that we think that this is how much of your power is used. So well, now we just did it for ring resonators. Now this is not one ring; it's an array of rings. And if you pump the system at the right frequency, not only you create a soliton in a ring, but also these since they're locked to each other, they will be a nested ring, nested soliton. So if you look at each of these rings, there is a soliton in it that is rotating, but overall there is also a soliton that is an envelope that governs the dynamic of the soliton. So you have two energy scales in the system. One is the energy scale that is associated with these rings. So it's a C over L, it's the free spectral length between different modes of the system. But also, since you have this collected modes, then you will have some features in between them. So these modes are the ones that I just showed you, this Hofstadter band, that you have the edge band and the bulk band, etc. So you have two different energy scales. That's why we call it the slow and the fast frequency. And then you get the solitonic decay. So this was just a numerical analysis in the system. Is that clear? Yes.
What is the bulk? You publish there?
We don't see synchronization.
Just like fading away.
Yeah. But I will show you a phase diagram in a couple of slides to tell you how much we know and how much we don't know. But it's an interesting phase diagram. The short question is that we don't know.
The solid is moving on the edge, but it's also going to the bulk.
It does not go to the bulk, yeah.
It's not
Yeah.
like a topological solid.
Yes.
Huh?
Yes. Yeah. Yeah. So in the linear regime, you would have expected, just if I had pumped the system in the linear regime, like weak nonlinearity. You would expect something like this, that you will pump one of these resonators and it would go around the system, and then after a bunch of round trips, it gets out. But now it's, you pump it at some specific frequency, it will create a soliton. It's just, the ring resonator just has a soliton inside of it. But now the soliton of this ring and that ring are locked to each other, such that it has this overall envelope. I hope it's clear with the light, right? So there is a, in each of these rings, you will have a soliton over here, soliton over here. But now this is also a soliton. It's a nested soliton.
But it doesn't move, you know? It's still-
It moves. I showed you. So it moves around the edge, but also in each of these rings, it moves, but we took a snapshot. You know, there is a fast time scale that these guys move at C/L. And then there is a slow time scale that is associated how the super soliton moves around the system, if you like, the super soliton. So that one goes with tunneling between resonators. And then the fast one is C/L. C, speed of light, L being the length of the resonance. So this animation is snapshots at C/Ls, such that in each resonator, they don't move. Inside the resonator, they don't move. You just see the collector.
How strong is nonlinearity for that?
So this is just numerics, right? But one can actually do it experimentally. So in silicon nitride, you have enough nonlinearity in the bulk that allows you to see this. And we think that it's more efficient, meaning that most of your pump is actually absorbed into this solitons, because the pump has more time to interact with your incoming light. And again, they're also robust. So if you remove one of the resonators, it would just go around it and then just continues it.
Just still in a simulation.
It's a simulation, now experiment. So the title change, it took us a long time, in particular, this gentleman who was, this was his main PhD work. For several years, he was working and sweating. So, it was not trivial at all to just go from experiment to theory. It took us 3 years. So this is what I just showed in one slide.
3 years.
Yes, yes, not a report there. Many rounds of fabrication, etc. So I cut that part, but was not trivial. So you pump the system, and then you send it to the sample, and then it comes out, and then you just put it on spectrum analyzer to see whether you have actually created this spectrum. You start with low power, you see something, it starts to grow, and then at some point it just starts to expand and goes over many 250 nanometer. This is in telecom, it's 1.5 micron. The power that you put in the system is crazy right now. You're putting like watts, tens and hundreds of watts in this. And so Chris actually burned a lot of things during this process. But what is important is I told you there is 2 time scales. One time scale associated with this fast time scale, so this space by C/L. But there was also a slow time scale, the time scale that is hops from one resonator to another scale, that is J. So these resonances, each of these contours have actually a lot of teeth inside it. So this is one like this, one like this, but this is actually a bunch of peaks and this is a bunch of peaks because of these 2 energy scales. And that's what we have. So in the first round, we could actually not resolve them because we didn't have a right spectrum analyzer. But now we can actually resolve them, that there is like basically large tooth and then small tooth that we have. Now, what happens if you have like a single ring, or if you tune it to the bulk, then you don't see that nested structure. You can also image it. So these are the imaging of the system. So we pump the system at this frequency, but we filter it out because we don't want the pump to interfere. So we only image the edge, and then you see that if you pump the bulk, then you will see some random shapes. Some of them have some patterns, I have to say, but some don't. And then these guys are confined at the edge, as you can see. Now, the phase diagram, that was the question that was asked. So if I change the frequency of my pump or change the frequency of intensity of my power, I have a phase diagram. In the middle is this chaotic region that does not have any meaningful shape, as much as we know. Maybe there are some, but we don't appreciate it. The super soliton and the Turing rod appears in a very small corner. We don't have any understanding of where these things happen. Again, back of that envelope or phenomenological model to understand where these things emerge. We don't understand what are the topological invariants of the system. So in a normal churn system, you have the bulk that is described by churn number, and the edge state would appear when you open it, but there is no theory of that. There are some efforts on it, but no theory. One can also do it in photonic crystals or other things. One can also think of it as its topological amplifier, because so far we just pumped the system with one color and then this cone came out. But then now we can come with another frequency and then look at it as a multiple amplifier. And I thought maybe there is some interest over here about that, because this is actually now, before I was not confident, like 3 years ago, because we just had theory, but actually now we're confident. We have some experimental data, so it's not all fantasy. So maybe actually these are serious amplifiers. Or multimode squeezing, because now we have all these features. You can look at the squeezing of different spectrum. So this is the nested team. I have to also say that it was like a big collaboration with, in particular, a group of Kartik, Srinivasa, and Greg, who helped us to understand frequency foam and to measure them and how to and hopefully the paper is revised and it's of the archive, but it's coming out in published form soon. So in the interest of time, are there questions about this part?
Yeah. So what can you say about the robustness, the nonlinearity? Does it remains the same as in the linear regime, or you don't know?
So robustness with respect to just removing a resonator or detuning, we have not done that. We are planning to do that. Now, robustness with respect to power. Imagine I change the power a little bit. It would go back to this phase diagram. So imagine that I'm going over here, how sharp this is, and how this goes from this just immediately goes from soliton to a chaotic region. I have to just give me another disclaimer. We have measured the frequency comb. We have not shown solitons yet. In order to show solitons, we have to show that it's actually no noise, that there is some phase locking going on. We have not shown that. And that's what we are working on. But is it like a sharp transition? What kind of transition it is?
Yeah, I still have a question about the amplifier possibilities, because I understand you never get to the regime where you can see parametric amplification of the signal field, right?
No. So we don't see that. So everything here is spontaneous.
Yes.
But then we are above the OPO threshold, such that we create all these side bands. But we don't have another seed to look at what happens over the seed.
But if you had it, you would observe some amplification.
Which we should see exactly.
Okay.
But we haven't explored that.
Okay, and also in that phase diagram, you always, I would expect to see for large pumping intensities some regime of like in the Duffin oscillator, a bright space or something like this. But I understand this is not possible here.
So this phase diagram is similar to the phase diagram of a single ring. So we were inspired by the phase diagram of a single ring, and we might be completely wrong. Just again on the record.
Okay.
So this is the phase diagram of a single ring, and inspired by that, we did numerics to find like the borders of our now large system. It does not mean that tomorrow someone actually digs and realizes actually this chaotic ring is way richer than what. And we actually experimented it, and numerically we see some patterns sometimes forming. But
your family has a single ring level, right?
Yeah.
Only one ring.
yes.
And when you pump in the bar,
No, we just choose the frequency. So I have a spectrum. So the spectrum is yeah. So this is like C over N, and being the length of this resonator, and then I have this bulk band and edge band. And this is this. So my pump is sometimes over here, sometimes, and then it will generate. Okay, no question. So where is this going? Going back to this phase diagram, there is of course this topological frequency cone that we are pushing. There is also an intriguing direction that the interplay between the topology of electrons and photons. Here we were just talking about photons, but of course electrons, quantum Hall, all that good stuff is there. So are there some interplays for that? Come to the next episode of this TV series. This is a recent experiment that we did. But a related question is like, imagine that we make these topological states of light with strong interaction. Here it was weak interaction, and get fractional quantum Hall states for the experts. So now this would be a little bit fast track. Imagine that we have a strong nonlinearity so that we get fractional quantum. How do you measure it? Because we don't have conductive measurement, etc. Are there some general ways to measure it? And that kind of brings us to quantum simulator that I will go very quickly over. So this is just a usual linear response that we do in condensed matter, but in quantum simulators, we have access to the wave function, so we can rule the world. Can we come up with some other ways to measure physical parameters? The usual way is the ancilla based. You have one ancilla and then you have a conditional Hamiltonian. And the way that you, depending on the way that you set up your problem, meaning that you have this ancilla and then you have the wave function and then you have a conditional dynamics, you can measure many things. You can measure either the properties of that many-body psi, or you can measure properties of the Hamiltonian, etc. You can measure topological invariance. And this is just a short list that I was involved in some of them. You can measure the topological entanglement entropy, you can do OTOC, whatever. But ancilla bases are cool, but difficult. They're coming. There's some experiments by Google that show it. What we were trying to do is there a way to measure, in particular, these Chern numbers, but not using ancilla based, without an ancilla, as an ancilla-free way of measuring the Chern number. This was a work a few years ago, but I wanted to advertise it here because I think there's some interest in it. In particular, we want to extract the Chern number for a topological system that lives on a disk. It's not on a torus, it's not on a cylinder. No experimentalist, at least now, will make it. So this was a collaboration with Peter's group And also my colleague makes some back actually at University of Maryland. So a very quick introduction to the Chern number is that you have a torus, you have periodic boundary condition characterized by two twist angles, theta x and theta y. You have your wave function, you vary theta x and theta y, you have a Berry connection, and then the many-body Chern number is defined as this Berry curvature integrated over theta x and theta y. That's the usual textbook thing. And once you measure this as an integer, you have to divide it by the degeneracy of the ground state. This is not always the case, but most of the cases is like that. And then you get your fractional conductance. And then you have examples of it. But what was realized recently was that you don't actually need to sum over all theta x and theta y. You can just go a little bit. There's a little patch and that's enough. But our work actually says that you don't even need to do that. You can just take one snapshot. So the goal of our protocol was this. I make a simulation in a quantum simulator. I hand you the wave function. I don't allow you to change the Hamiltonian, perturb this state, etc. I just give you like 10,000 copies of the wave function. Can you extract the many-body chain? So it was a conceptual question, apart from like its experimental relevance. So the idea is just basically to understand it a little bit is the generalization of the Resta formula. So what is it? Is that I have this Corvino geometry, and if I want to follow up an argument, is that I pierce a flux to the system, it generates an electric field, and since I have a non-zero sigma xy, I would have a transverse current. So if you have a current from E and M, we know that we have a non-zero derivative of the polarization because charge is conserved. So non-zero current means that the polarization conserved. So you can, instead of measuring the current, you can just measure the polarization and then see how this polarization change. In particular, if I just want to look at the polarization in the y direction, if the system is periodic, you cannot use y, you have to use e to the I y over L. And this was the breakthrough of Smith and Vanderbilt. So if I want to write it in one form, is that what you need to do is that you have your wave function for a specific flux. And then you need to evaluate this e to the I L, which is this basically the polarization. We have to see how the system polarization changes as a function of phi. That's the rest of the formula. But as I said, you need to have the wave function for different values of phi. But what we realize is that you can actually have a formula that does not depend on phi. You can simulate the effect of phi by applying some operator and then measuring the swap, like something completely here. So I give you this wave function psi in black, and then you apply these red and green operators, and then you measure the swap, and then it should give you the Chern. So these are so this basically what happens is that these V and W, these operators will give you polarization and this magnetic flux training. So instead of changing the phase of the boundary condition, you actually apply an operation, and this swap is responsible for taking your system from a disk and simulate it on a torus. So it synthesizes the effect of the torus. So why it is like that? If one has to go to TQFT a little bit, but like a very quick refresher is that the topological properties don't depend on the deformation of the system. So we have the TQFT, topological quantum field theory, and you can think of them as a path integral. So this is in time and this is in space, it's 1 plus 1d. And you can think of it actually as a matrix product state that you're contracting your psi on top and psi on bottom. But now you have more indices, you have time and space. So here, if you're in 2D, your state is living on a torus. So it would be just a contraction of. But let's just take an example. Why the swap operator would make a torus on a disk. Let's just start with this. So this is my psi, and this is like bra psi and ket psi, and I contract them. Again, think of matrix product state. That these are two states that I want to contract at this position, this position, this position. So if I just contract it, usually that would be my usual packet. But now I want to do a trick. I want to identify these ones with these ones, these ones with these ones. So what happens is that if you do that, you have this eye opened over here, eye opened over here. But then I want to identify these guys with these guys. So I start to rotate this one 180 degrees. And then I identify the double arrow with double arrow and one arrow with one arrow. So that would create a handle. So application of a partial swap on part of your system, it basically means that you have created a handle on the system. So I started with the sphere and then I ended up with torus. You can start with any other geometry and then apply this partial operation, and then you can create a handle. Once you have a handle, you thread a flux inside the handle, and then you get your response. So that's basically the whole thing. This is like 2-copy version of it, but it's just the same trick really. Like playing with this, we can make it with 2 copies. So here we go longer systems. So I don't want to take some time because it's before lunch and you may get angry at me. But that's basically pretty much it. And then once you realize that you can do this, you can go. Zipe, my previous student, he did the PMRG fractional quantum Hall on all kinds of states known to humanity to make sure that this formula actually works. So we had the TQFT motivation, but also numerically it matches everything.
Maybe, no, how to measure like that.
Yeah. So how to measure it is that the key is that W and B, that's from local operation, and the swap. And swap reminds us of what André Selvens and Benoit and Peter have been doing. So we should combine them together, and that's why you combine them.
And the other operator was like a local phase on the.
So this is the protocol.
Oh, okay.
So the protocol is the following. I have system A and system B. Does not have to be in the same time. They're just rotate like this. Then it doesn't have to be also cylinder. Can be square. In the paper, we actually did square. You apply some local operation. Okay. Just density operation. So it's just measuring. Then you need to apply some random operation that it will simulate the swap. Then you measure in the Z base, and then you just do that many times, and then you just post process. So if you are familiar with Peter's group's work, is that they usually look at this statistical correlation, and then there is this O that one has to take care of. That's just some birthday paradox numbers that appear over here. The invention over here is that you have to put these numbers inside. So one can actually do the experiment where it's just after the post-processing, one has to use these numbers and this phi such that it can simulate the threading of a flux. So one doesn't not need to do new experiments to simulate the threading of a flux. It's just all in post-processing. You process it once with phi, once with phi plus epsilon, etc. Then once you have that, you take the derivative. So the protocol is very similar to the usual randomized.
So we don't actually put the flux.
No. Yes. We don't put the flux and we don't make it torus. Or we just create this handle. And it works in a 6x8 system. Actually, it's kind of interesting because you were asking how small of a system I should have such that I have a reasonable bulk and I can associate with bulk. So it kind of answers that question as a side note. And then how many measurements you need, of course, is exponential, but in the subsystem size. You're swapping these two subsystems. You're not doing the swap of the entire system to two subsystems. Yeah. So with that, I hope that I have motivated a little bit these things. This is one formula. I hope that there is just this is like a tip of an iceberg. that there are all kinds of other observables that one can use by doing swap. This parameterization in matrix product state, we can do all kinds of contractions. What do they mean? What do they correspond to anything physical or not? So with that, thank you very much for your attention.
Okay, so are there any questions?
In that example, you don't have any flags and no flows, what is topological, then the system?
So you don't have to have a state on a torus to be topological. So you have like a I don't know, fractional quantum Hall state that people measure in the lab, they are not on a torus. So you have a system that has the bulk has some topological property. Usually it's manifested as the edge property. And then by measuring the edge property, you know that the bulk has some topological property. Sounds good? Now, here it's kind of like a direct way to measure that the order of the state in the bulk.
What is the smallest hole you have to do in this case?
Yes, sir?
The smallest hole you have to find?
Good. Yes, that was a long discussion actually in the paper, like how small or how large these sub areas should be. So if there are some correlation length associated with this topological, or let's say this fraction quantum Hall, that would be magnetic length. So the subsystem size should be of the size of the magnetic. It should not be much bigger or much smaller. If it's smaller, it doesn't work for sure. If it's much bigger, it doesn't also work because you're doing swap, partial swap, and it exponentially goes down, the overlap. So, because you're breaking all the EPR pairs and looking at the many body swap, or many body swap always.
More questions? No, let's thank Mohammad again.
Just to remind for those of you, he will be here for 2 weeks.
Yes, exactly. Yes, please
Yeah.
have lunch.
Tranquilo.
Many.
Yeah, I think this last point was
That's very good. And they should expect which one, which is very similar, the PRP or which one? The one of the many body variants.
yeah, so there is a PRV, just to, there's the numerics and the TQFT part, and then there is a PRL that was with Peter's group.